this video lecture, we shall discuss the information derived from rotational spectra. Microwave spectroscopy is used to determine the structure of molecules, including the geometry of bonds. It can also be used to study the properties of hydrogen bonds, including proton transfers through hydrogen bonds. Microwave spectroscopy can be combined with other electromagnetic radiation fields to perform specialized experiments. These experiments are called double resonant experiments and can help obtain information about collision energy, transfer rates, and mechanisms. One can get the detailed molecular structure of any diatomic molecule from rotational spectra. The rotational spectra of a substance at room temperature can be examined accurately. Perhaps the most important information that one can get from rotational spectra is details about molecular structure. Rotational constants can be obtained with very high accuracy. Information about the position of atoms in a molecule is obtained from the three-dimensional constants from which the three principal moments of inertia of the molecule Ia, Ib, and Ic can be obtained. Information on molecular structure, internal motions, and intermolecular interactions are easily obtained. In the presence of an electrostatic field, there is a stark splitting which allows to determine molecular electronic dipole moments. Microwave spectroscopy is suitable for studying chemically and physically very interesting molecular systems, including weakly bound complexes, radicals, ions, and other transient species. Information on molecular structure, internal motions, and intermolecular interactions are easily obtained. Structure. Rotational spectroscopy is a high-resolution technique that can provide structural information about molecules such as their moments of inertia, dipole moment, nuclear quadrupole hyperfine structure, quadrupole coupling constants, centrifugal distortion parameters, spin rotation constants, and the information relative to electron distribution and bonding. Bond angles. Rotational spectra can be used to characterize the bond angles. Atomic masses. Rotational spectra can be used to determine atomic masses. The electronic structure. When a fine structure or a hyperfine structure can be observed, rotational spectroscopy can provide information on the electronic structures of molecules. Internal motions. Rotational spectroscopy can provide information about the internal motions of molecules. Intermolecular interactions. Microwave spectroscopy can provide information about the intermolecular interaction of molecules. Electron distribution. Rotational spectroscopy can provide information about the electron distribution of molecules. Weak molecular interactions. Rotational spectroscopy has been used to establish the nature of weak molecular interactions such as van der Waals, hydrogen, and halogen bonds. Chemical composition of the interstellar medium. Rotational spectroscopy is used in radio astronomy. Atmospheric chemistry. Rotational spectroscopy is used to measure chlorine monoxide, which is important for atmospheric chemistry. Radio telescopes. An important application of rotational spectroscopy is in exploration of the chemical composition of the interstellar medium using radio telescopes. Electronic spectroscopy is able to detect the presence of various atoms, ions, and a few radicals in the light of stars, but recently simple stable molecules in space detected by using microwave spectroscopy. RF astronomy. So far, 130 molecules or ions have been identified in interstellar space by the rotational emission spectra. In diatomic molecule, there is only one observable, the moment of inertia, which along with atomic masses gives the interatomic distance, which is given by I equals the moment of inertia, which is given by mu r squared, where mu is the reduced mass, r is the bond length. So r is given as I times 1 divided by m1 plus 1 by m2 to the power 1 by 2. Here m1 and m2 are the masses of the two atoms in the diatomic molecule. A linear molecule of n atoms has in general n minus 1 bond distances to be determined. For example, when you take two atoms in a diatomic molecule, there will be one bond. Suppose you are going to take 3 atoms in triatomic molecule, there will be 2 bonds. So similarly, n minus 1 bond distances to be determined. In this case also, only one of the bond distances can be obtained from rotational spectra. However, the additional n minus 2 bond distances have to be obtained by isotopic substitution, as interatomic distances are invariant under isotopic substitution. For symmetric top molecules, only one of the moments of inertia can be obtained from the rotational spectra. Therefore, one requires the rotational constant of many different isotopically substituted species, as there are unknown structural parameters. For asymmetric top molecules, it is possible to get all the 3 principal moments of inertia from rotational spectra, which can give only 3 molecular parameters. The additional necessary equations to determine all the parameters have to be obtained by determining the moments of inertia of isotope species of the same molecule. When it is not possible to get sufficient isotopic combinations, the combinations of microwave data from other sources is done for unambiguous determination of structure. At this stage, probably it is appropriate to distinguish between the hypothetical equilibrium distance, which is given as Re, and the average distance in the ground vibrational state, which is given as R0. The distance Re corresponds to a hypothetical vibrationless state of the molecule. However, in the ground vibrational state, the molecule has a vibration energy 1 by 2 h nu, and R0 value obtained from B0, which is an average value of interatomic distance over the vibration. The bond distance Re can be calculated from the value of Be. The Re value does not change with isotopic substitution. However, R0 depends on isotopic substitution. Thus, the molecular constants can also be determined from rotational spectra. The force constant of a bond can also be determined from the values of rotational constant B, and the rotational distortion constant D is the relation between D and B, and nu bar is given as this expression. So nu bar squared equal to 4B cube divided by D, where nu bar equal to 1 divided by 2 pi c root of K by mu. The force constant K is then given by K equals 16 pi square c square mu B cube by D. Thus, the force constant of the bond can be determined from the values of rotation constant B and the rotational distortion constant D of any molecule, of any diatomic molecule. Dipole moment. Information about the dipole moment. Precise determination of electric dipole moment is possible from microwave spectroscopy by the measurement of Stark effect. Arrangements exist to measure dipole moment values as low 0.05 dB. Moreover, the Stark effect data give the value of dipole moment in the appropriate vibrational level. Dipole moments can also throw light on the nature of molecular bonds determined by microwave spectroscopy. One can also determine the moment of inertia of any diatomic molecule using the relation B equals h divided by 8 pi squared Ic, and thereby I equals h divided by 8 pi squared Bc. B is taken from the experimental data of any rotational spectra. We can determine the bond length of any diatomic molecule. I equals We know that I equals mu r square, and mu is given by this expression. So r equals root of I by mu. So if we know the value of I and if we know the value of mu, one can get the bond length, the value of bond length of any diatomic molecule. Thus, the rotational spectroscopy can reveal information about the rotational energy levels and derive key parameters such as bond lengths and angles. Microwave spectroscopy has provided the detailed structure and associated parameters for several thousand molecules.